Find the first four partial sums and the nth partial sum of the sequence given by a sub n equals 2 times n minus 1. Let's look at what the first few terms are, and then we can look at the partial sums and see if we can find a pattern. The first term, a sub 1, is going to be 2 times 1 minus 1, which will be 2 minus 1, which is 1. The second term is going to be 2 times 2 minus 1, which will be 4 minus 1, which is 3. The third term is 2 times 3 minus 1, which is 6 minus 1, which is 5. And we can see here that the terms of the sequence are the odd numbers. 1, 3, 5, 7, 9, 11, etc. But we're more interested here in the first partial sums. So let's look at the partial sums. We know that the first partial sum is just the first term, which is 1. The second partial sum is the sum of the first two terms. 1 plus 3 gives us 4. The third partial sum is the sum of the first three terms. 1 plus 3 plus 5 is 4 plus 5, which is 9. The fourth partial sum is the sum of the first four terms, which is 1 plus 3 plus 5 plus 7, which is 9 plus 7, or 16. And when we look at the partial sums that we have here, we've got 1, 4, 9, and 16. You probably recognize these numbers as the perfect squares. So the first partial sum is 1 squared, the second partial sum is 2 squared, the third partial sum is 3 squared, the fourth partial sum is 4 squared, and we can follow this pattern to see that the nth partial sum is n squared. It's interesting because it isn't clear by looking at the original formula or by looking at the terms of the sequence that the partial sums are going to end up being the squares of the whole numbers. However, we actually can look at this geometrically. If we look at 1, we're going to look at little squares here. So 1 square is 1 times 1. Then if we add 3 more, we can add them in particular like this. And so we can see that this actually gives us a 2 by 2 square, which gives us a total of 4. Then the next one to add is 5, and we can do that by adding another row and column here. If we add 5 more squares, 1 plus 3 plus 5 ends up giving us a 3 by 3 square, which of course is 9 units in area. And then after that, we can add 7 by adding another row and another column. And so you can see how the perfect squares are actually the sums of the odd numbers. It's just an interesting geometric argument, nothing that you would be expected to do for a problem like this. I just wanted to show that there is a geometric explanation of why we get the perfect squares here.